A few weeks ago, hundreds of intrepid people set out from the UK to study one of the coldest regions of our planet, Antarctica. In Antarctica, spring is just starting, which means that it's getting warm enough for scientists to do their fieldwork. The scientists are working to understand why the natural processes and animals there are so important to the rest of our planet. They include Nadine and Roseanne, who set off on board the UK's polar research ship, the RRS Sir David Attenborough, and David and Simon, who travelled to Rothera Research Station on the coast of the continent of Antarctica.
It's so cold. It's so cold not just because we're in Edinburgh, which is freezing today, but we're back in our polar room here at Dynamic Earth. Look at that, we've got a real iceberg.
Yes, I can contest to that because it's freezing in here.
It's really good. Now, when we talk about climate science, we talk about ice a lot, don't we? We're constantly talking about the polar regions. Quick question for you.
Yep.
Why are those polar regions so important when it comes to climate change?
Well, one of the reasons is that ice is really good at reflecting back sunlight. And as we start to see the Earth warm and we start to see the amount of ice that we have decrease, that means that more of the sun's heat will be absorbed.
Yeah.
And so this is a bit of a runaway effect where we have more heat absorbed, we heat up more, we lose more ice, and so more heat is absorbed from the sun. And so
those kind of polar, they're almost like the canary in the coal mine. We can tell a lot about what's happening with the state of the planet by looking at those ice regions.
Sure,
so ice is very important.
Yeah.
Now then, you have just been in Antarctica, which is an amazing thing, because not a lot of people go to Antarctica. It's generally just scientists, which is the way it's meant to be. We like to protect Antarctica, but you went there.
Yes.
What was it like? Because I'm massively jealous.
Yes, I was in Antarctica. I came back actually just under a week ago, just a few days ago from Antarctica itself.
So you're acclimatised to this?
Yes, I'm fine actually.
Was it massively freezing?
Yes.
Okay.
Very, very, very cold. I went to the Antarctic Peninsula, which is a really sensitive area actually. Lots of science happens in the peninsula, and there are lots and lots of animals down there too, which people are working to protect. And
penguins.
Environments. I saw many penguins.
Good.
They're so comical, these penguins. They're amazing. Penguins, whales, orcas, seals.
Well, you are perfectly placed now, because we're going to go live to the research ship, Sir David Attenborough. I'm not quite sure who we've got. Can you hear us, Sir David Attenborough ship? Wave if you can hear us. They can hear us.
Great. So we're gonna pass over to Andy, and he can ask all the questions.
Yeah.
Thank you, Andy.
It's all yours.
Thanks, guys. That must be the dirtiest iceberg on planet Earth, I'm pretty sure. I wouldn't lick it, but there we go. Anyway, so welcome to Northumbria. So we're going to give you a polar themed session today, and we're going to talk about how we monitor Earth's ice, why we monitor Earth's ice, and how we monitor it from space. So there's a bunch of us here. I'm going to start by giving a quick introduction to the people that you're going to hear from in this blog. It's me, myself, Andy Shepherd. I'm head of department in geography at Northumbria Uni. Sammy Buzzard, she works here as well. She's going to talk about Earth's ice. Anne Brackman-Fogman is in the Arctic right now. She's in Tromsø, so just north of Tromsø, and she's actually closer to the North Pole than the Rothera base is to the South Pole. So she's the most Arctic person on today's session, or most polar person on the session. And we're going to talk to Megan Christian, who is ESA's candidate astronaut. So she's going to talk to us later on. So I'm going to hand over to Sammy first of all, and she's going to tell us about Earth's ice.
Hey, thanks, Andy. So here we can see a slightly unusual way of demonstrating how our polar regions work. But for those of you who play Minecraft, so this was created as part of Frozen Planet 2, which was on BBC last year, but I think it's still on iPlayer, so I could totally recommend if you missed it, going back to see that. But this shows us not only the huge variety of things that are going on in the polar regions, all the different types of ice and land features, but also the wildlife that lives there. So this is, of course, incredibly important habitat for creatures such as the orca we just saw. We've got a seal. I think there's a walrus coming up. Yeah, there he is. And of course, the polar bears and penguins that we hear all about as well. Now, when we talk about the polar regions, just to make sure we're all on the same page, there are two main areas we're often talking about. So up here, we've got Antarctica, which is the South Pole. So this image on well, it's my left. I'm not sure which way the screen's flipping around for you, but the one with the big white bit in the middle is Antarctica. So we're looking up at the Earth from below, as it were. And Antarctica is mostly land surrounded by ocean. We can see some kind of white stuff that builds up and disappears with the seasons. This is sea ice, which is frozen ocean, which we'll come to in a second. But looking at the opposite image, so looking down at the top of the Earth now, you can see that the Arctic is, no pun intended, the polar opposite of Antarctica, because it is ocean surrounded by land. So you can see that there are some land masses. Greenland is just here. That is covered by ice the whole year round, but lots of the Arctic gets snow just in the Arctic winter. So one of the very important features and one of the most vulnerable features of our polar regions, and actually ice that's found in every continent, some of you may have been lucky enough to, for example, visit the Alps in Europe, are our mountain glaciers. And glaciers are really important because they are water resources for people. And so a lot of people use these not just for recreation purposes, maybe some of you have been skiing in areas with glaciers, but for their water supply. And because the glaciers are much smaller than those big land masses, Antarctica and Greenland, they're much more vulnerable to changes in our climate. So these are the areas of ice that are disappearing most quickly. I mentioned earlier sea ice, which is our frozen ocean. And you heard in the intro about how important it is that ice is very white and reflective. So if we lose our sea ice, you're left with dark coloured ocean, which isn't going to reflect as much energy back to the sun as the ice would. So at the moment, the polar regions are acting to cool our planet. They're really important for that. But if we lose them and we get kind of darker land or ocean underneath, then that's bad news for everyone. The sea ice is also really important as habitat. So polar bears use it for hunting, and also in terms of shipping, because actually we can get around the planet more effectively if we know where the ocean is going to be frozen and where it isn't. Now, Greenland is the big mass of ice in the Arctic. This is somewhere I spent most of my summer, and Andy's been there several times as well. And if you're coming to the maths session later, you can hear lots more about how it's melting on its surface and how we use maths to investigate what's going on in this kind of huge frozen area. But this is an area where people live, and also there's lots of incredible wildlife there, so somewhere we definitely want to protect. Now, the biggest area of ice on our planet is Antarctica. About 70% of the Earth's fresh water is in frozen form, and 90% of that is in Antarctica. So this is where all the ice is. It's kilometers thick in the middle, and some of it's been there for thousands and thousands of years. So there's a lot of important ice locked up in Antarctica. We want to keep it there. And one of the key ways that it's currently protected from coming off of that continent is through ice shelves. So most of Antarctica is ice sitting on top of the land. When the ice flows and reaches the ocean, it remains floating on the ocean. But these ice shelves at the edge of the continent act to protect the rest of the ice that is on Antarctica. So they're also a really important area of Antarctica. Now I'll hand back over to Andy, who can tell you more about how we're monitoring these areas.
I can. Thanks very much, Sammy. So we use satellites. This is the first satellite that was launched from Earth into space, Sputnik 1 in 1957. Didn't have any sensors on board, but it started the space age, really. And the first satellites that we launched after that were to look into space. But actually, we learned in the 1990s that we needed to know much more about Earth. And so we developed a bunch of sensors that could monitor different parts of our planet. And Cryosat is one of those. It's the European Space Agency's polar mission. And it was designed in the early 1990s, late 1990s, and eventually launched in 2010. And it's been flying in space since then. And we performed an important operation last week to extend the satellite's lifetime by another 5 or 10 years by fixing a leaking fuel pump that was losing fuel into the space and was threatening the lifetime of the mission. So we've been monitoring Earth with Cryosat since 2010. It's about 13 or 14 years worth of measurements, and that gives us enough measurements to paint a picture of what's happening. So this is an animation of some Cryosat data to show how Antarctica is changing over time. What we found is, as Sammy said, it's the biggest mass of ice and store of sea level potential on Earth. It's melting, it's thinning in West Antarctica, and that's pouring more ice into the ocean and causing sea levels to rise. Well, if you look around the rest of the planet, and we can do that because the satellites look everywhere, we can see there are changes in all corners of Earth's cryosphere. So we see that the ice shelves in Antarctica are losing about 300 billion tons, gigatons, billion tons of ice per year. We see that the sea ice in the Arctic is losing about 300 billion tons of ice per year. We see that mountain glaciers all around the planet, about 260 billion tons per year. We see Greenland, 160 billion tons a year, and even the Antarctic ice sheet, 110 billion tons per year. The last component of the cryosphere is Antarctic sea ice, and we've heard a lot about that recently. That's also shrinking as well by about 40 billion tons per year. What does that mean? If you play Minecraft, back to Minecraft, this is a wonderful animation of Antarctic research bases that some very clever young men designed and built a couple of years ago. And each one of these cubes is about 1 meter cubed. And 1 meter cubed is a ton of ice. That's the easy way to think of things. So 1 ton of ice is a meter cubed. 1,000 tons of ice is just 10 meters cubed. And 1,000,000 tons of ice is 100 meters cubed. But we need to go much bigger than that to count up how much ice is being lost on our planet, because we're losing 1 trillion tons of ice per year all around the planet. And that's a 10-kilometer cube. This is a picture of what that would look like next to London for scale. And that's happening every year. We're losing 1 trillion tons of ice per year because the polar regions are melting, either because the air is warming or because the ocean is warm. And that's a real problem for people who live in coastal areas. It causes sea level rise and coastal erosion. This is East Yorkshire, where I live. And the coastline is eroding. We can't live there forever, but we depend upon our coastlines for recreation, for shipping, for commerce, and just people's homes. This is actually one of the important parts of the UK where people grow food, and we need access to these areas. And we're going to have to perform a managed retreat in some places. In cities, sea level rise is even more devastating. This is the flood that hit New York City in 2012 when there was a hurricane sitting over the island of Manhattan, and it flooded 50 square kilometers of land and damaged 20,000 properties. And in fact, many people died in this event. This will happen much more as a consequence of sea level rise, and we need to think about what we can do to solve that. There's lots of things you can do as individuals to make a difference. You know most of these. We can use renewable electricity. We can eat less meat. We can fly less. We can actually plant trees. That's the #1 climate solution. Planting trees, using solar panel power, and using wind power are the top 3 climate solutions. You can change the way that we're governed by voting, or you could protest. But if you're interested in science, there's lots and lots you can do. So we need to build better models of how Earth's ice will melt in the future. And that has to happen before we can convince people to do something about sea level rise, because there's lots of uncertainty about how much sea level rise we might see by the end of this century. We can build new satellites. That's a really exciting thing to do. We need people to build the next generation of satellites, design them and get them into space so that they're monitoring the Earth's polar regions when Cryosat eventually dies. And it won't live forever. It was only designed to live for 3.5 years. It's lived for 13 years. We can protect our coastal regions. This is the sea level defense plan for Manhattan Island, and other cities and countries have similar things. Or we can use renewable energy. This is a hydro plant near where I live, and it was built at a cost of £5 million, but it powers 800 homes. So this costs almost nothing compared to the price of an actual home, and we should do much more of this. So there's lots of things that we can do to help, but there are still lots of problems that we need young, smart scientists to work on. And with that, I'll hand over to Anne, who is a young, smart scientist in Tromsø.
Thank you, Andy. Can you share my slides? So yeah, I'm gonna start. So I'm a researcher at the Arctic University of Norway in Tromsø, which is high up in the Arctic, as was already mentioned, high above the Arctic Circle, actually. We do have a lot of snow here also. And I've done my PhD work with Andy Shepard, and there I've looked into icebergs specifically, and the really big ones in Antarctica. So an iceberg is basically a very large chunk of ice that has broken off an ice shelf or a glacier and is now floating in the ocean and drifting with the ocean currents. And they can be really, really huge. So they can be up to 300 kilometers long, which is longer than from London to Manchester. They can be up to 600 meters thick. Okay, I'm just going to share my slides so you can actually see it. Have you got them? Okay, so this was my just a brief map of where Tromsø is. You can see how it's located high above the Arctic Circle, far more north than the UK, for example, similar latitude to Greenland, which we've already heard about, and first picture of a tabular iceberg. And then here you've got another image of a really huge iceberg in Antarctica. And we've already heard about sea ice, for example, which is the frozen ocean. And you can see that the iceberg sticks out a lot higher above the sea ice and the ocean. So yeah, I just said they can be up to 300 kilometers long. They can be up to 600 meters thick. About a tenth of it is above the ocean. So normally they may be 300 to 400 meters thick, and then 30 to 40 meters roughly are above the ocean. But it's really large. I think it's really hard to imagine. I think the comparison to some sea ice and orca whales gives you maybe a sense of a scale, but yeah. And one example iceberg that was in the media a lot is the A68A iceberg. So you can see both on the map and on the animation how it drifted from the Antarctic Peninsula is where it broke off from or calved, and first drifted through shallower waters and then got onto the deeper and warmer ocean. And at the end of its life, it approached the island of South Georgia, where we've also got this image on the top left. You can see the iceberg got really, really close to the island, and it's basically the same size as this island because this iceberg was so huge. And there was a worry that the iceberg would ground there. You can also see in the animation, it got onto the shallower parts near the island. Luckily, it didn't ground because then it could have blocked like access for the penguin colonies there, for example, to their feeding grounds. What it did do is it melted near the island. It released a lot of fresh water and therefore impacted the ecosystem there, but rather in a positive way because it fosters biological production. And in this animation, you can see how the iceberg slowly melted from underneath and how it broke into pieces during its several years of lifetime. Especially towards the end, you can see a big breakup event, and that the melting from underneath is really accelerating. And we can measure all of this from space with the satellites. And then the last technique I'm going to present is artificial intelligence. So artificial intelligence can help us to automatically map these changes in iceberg area, for example. And on the animation, you can see some satellite images of this iceberg and how the neural network was trained to map the outline of the iceberg and therefore also the changes in area automatically. And in each step, the prediction is refined a little bit. It gets a little bit better until eventually we get the perfect outline of this iceberg automatically. And before, you would have to draw it by hand, which is, you can do this, but it takes a lot of time. And I think it's a big improvement that when we can do it automatically. And once it's trained, it only takes 0.01 seconds, so really fast. You can also see from the animation how the iceberg shape changes, how it's breaking apart and traveling through all the different environments as it gets north. Yeah, and with that, thank you very much for your attention. And I'm going to hand over to Dr. Megan Christian, who is a reserve astronaut at ESA and the Exploration Commercialization Lead of the UK.
Thank you very much, Anne. I'm going to share my screen for you as well. Just one moment, here we go. So I'm going to take you to a different part of Antarctica. We're going to go to Concordia Station, which is a French-Italian base in the middle of the Eastern Antarctic Plateau. It's on about 3,200 meters of ice. So the altitude is quite high. And I'm going to make this video go. This is the base here. It's made up of two towers. There's a quiet tower and a noisy tower. And I just wanted to highlight to you the kind of science that goes on there. We're far from the coast, so not looking into icebergs at Concordia Station, but there are lots of experiments going on into astronomy and astrophysics, atmospheric sciences. In fact, I was there to do atmospheric physics and meteorology back in 2019. I was there for a whole year. Earth sciences, glaciology, human biology, and remote sensing. And in fact, the location was chosen to do an ice core drill because it's on so much ice. So they made an ice core of 3 kilometers long, and then they cut it into little slices, and they could analyze the air that was inside those slices, little bubbles of air. And that can give information on the composition of the atmosphere going back 800,000 years. And that's how we know that in the last 100 years, the amount of methane and carbon dioxide in the air has gotten extremely high. I just wanted to highlight a few little things about Concordia Station. So in the bottom left here, I'm showing the coldest day that we had while I was there. So we got down to a wind chill factor of minus 104 degrees Celsius. So it's an extremely cold location. It's also a low pressure area. So at sea level, we're used to having a pressure of 1,000 hectopascals. But at Concordia Station, it gets as low as 600, 610 hectopascals. This day was a reasonably high pressure day. But that means that you're breathing about 65%, so 2/3 of the oxygen that you would normally breathe at sea level. So you can kind of see that does strange things to the body. You also have a really low humidity. It's so cold that the air just can't hold very much water. And you also have 100 days where the sun doesn't go below the horizon and 100 days where it doesn't come above the horizon. So 100 days of night. And for all these reasons, the European Space Agency does studies there. So this is a completely different study to the ones that we've been talking about before. Concordia Station is also known as White Mars because of its location, because of its altitude. And for those reasons, it's very similar to what a long duration mission to the Red Planet would be. So every month, the Winter River researchers that are there, and this was including myself a few years ago, we're subjected to a lot of different experiments. So we have blood samples taken, urine samples, stool samples, a bit of everything to just see how our bodies go over time. We also have cognition tests. They do experiments to see what kind of foods we're eating, whether exercise could mitigate some of the bad effects of being in an isolated, low oxygen environment like that, and also cognition tests. So one of the interesting ones was we learnt how to dock the Soyuz capsule, this is the Soyuz capsule here, onto the International Space Station using a simulator. So you can imagine that if you're going to Mars, you learn to land on Mars when you're on Earth. But what happens during those 6 to 9 months that it takes you to travel there? Does your brain retain that information? Well, most likely not. So this study that we were doing was to see exactly how much we retained. So that can help the scientists to design what kind of educational programs, what kind of training needs to be done while you're on a long-term mission. So lots of interesting studies going on in this incredible place that is Antarctica. Thank you.
Fantastic.
Megan, thank you very much indeed. Oh, I don't think I could cope in Concordia Base for a year. I think I have the wrong stuff to be an astronaut. I think I'd go crazy. Right, from Concordia Base, we're going to go to the RSS Sir David Attenborough, which is currently, where is it in the world? Do we know?
Well, let's ask. Let's find out.
It's a research ship, and we've got the scientists on board to tell us a little bit about what they're doing. Over to you.
Hello.
Hi.
Good morning.
Can you hear us?
Well, welcome. We can hear you. We can hear you fine. Can you hear us okay?
Yes,
perfect. Tell us where you are first.
Well, we're here in Antarctica at the moment. We're coming to you live from the deck of the Sir David Attenborough research ship as we sail through the Southern Ocean that surrounds the continent of Antarctica. So my name is Roseanne and this is Nadine, and we are both scientists with the British Antarctic Survey. And as you can see through our window here, it's pretty chilly morning here today. I'm just going to adjust the camera so you can see. We have icebergs floating past our ship. And we've got a lot of fog conditions as well, so it's quite difficult to see what's going on here this morning, but we've been enjoying watching icebergs gliding past the ship all morning. It's about freezing point here, so it's about 0 degrees is the air temperature. Now it's actually springtime here in Antarctica. And of course, in the winter months, the sun often never rises above the horizon at all. And the temperature actually plummets much further than today, to as low as around -20 or -30 or even lower than that. And this extreme cold in winter has a huge impact on the ocean surrounding Antarctica. The surface of the ocean actually freezes over to form a solid crust of ice that we call sea ice. And this sea ice could be several meters thick, and it covers many millions of square kilometers, so that the area of Antarctica almost doubles in size every winter. And now that we're in springtime, the days are getting longer and the air temperature is starting to rise. And that means that all of that sea ice is beginning to break up and melt away to reveal the ocean beneath. So we've timed our arrival here perfectly to study this epic seasonal transformation.
So the springtime is a really exciting and important time of year in the Antarctic. The Southern Ocean literally bursts into life, and it's fueling the vast populations of wildlife that feed and breed here during the summer. And this is all linked to the melting of the sea ice. So we're here to learn more about this chain of events and how the sea ice and the ocean and the biology all interact. So firstly, we're going to explore the physical conditions of the water column from the surface right down to the deep waters below. Secondly, we'll trace the flows of nutrients that are released from the melting ice into the water column. And thirdly, we'll examine the growth of microscopic marine plants known as phytoplankton, which rely on these nutrients and water conditions to flourish and grow. And tiny animals like zooplankton, which feed on the phytoplankton, and in turn support a range of Antarctic predators, including fish and squid and penguins and seals and whales. And understanding how these spring processes work is really important, because these tiny plants and animals not only support life in our oceans and economies like fishing and tourism, but crucially, they also help regulate our climate by removing that carbon dioxide from our atmosphere. So to examine these spring processes, we'll be heading down to the Weddell Sea, which is a really, really cool part of the Antarctic, full of sea ice. We're going to sample along a really long line called a transect from the open ocean right into the thick sea ice, where we will be deploying robot gliders under the sea ice, and we'll be putting sensors fitted with these water bottles called a Niskin bottle, hope you can see that there, into the water column to collect information on the physical properties of the seawater, such as the currents and the temperature and the salinity, the nutrients and those phytoplankton. And we'll also be jumping off the ship onto the sea ice to collect samples of the sea ice itself with a corer like this to look at the phytoplankton living within it. And finally, we'll use two types of nets, curiously called the bongo and the mammoth, because they look like a bongo drum and they are actually mammoth, to collect samples of zooplankton down to depths of up to 1,000 meters.
So the Sir David Attenborough research ship has been really carefully designed to make it possible to do this kind of science research in the extreme environment of the polar oceans. And for example, this ship is actually an icebreaker ship, which means that it's able to move and crush into the ice, into the sea ice, so that we can gain important measurements within the sea ice zone itself. Now, the data that we're collecting is vital to help us to build a more complete picture of the health of our oceans now. Because if we know this, we can begin to predict how the oceans might respond to climate change in future and what we can do to help. Now, the research being done by scientists at the British Antarctic Survey is not limited to this ship. Back on land in Antarctica, we have several land-based research stations that are gearing up for a busy summer of science research. So let's hand over now, if we can, to Simon and David, who are joining us live from the largest of these research stations, Rotherham. Simon and David, can you hear us?
Hello, good morning. Yes, we can hear you. Can you hear us?
Yep, we can.
Yes. So welcome to Rothera Research Station. So this is the biggest of the British Antarctic Survey research stations, up to 170 people during summer, 20 to 30 people during the winter. So it's a very, very busy place at this point in time. Most people get here by flying in a plane. So we have a de Havilland Dash 7 plane that flies in, brings people here to the station. But the Sir David Attenborough just came and visited here, and we actually got to meet Nadine and Roseanne. But they also bought a bunch of scientists, but they also bought much of our cargo, much of our supplies for the next year. Pretty much everything we need comes in on the ship in a couple of calls during the year. But when I arrive here, many people get in a plane, fly off into the deep field. When Andy Shepherd was here last year, he was in the plane, measuring the thickness of the ice, calibrating the satellites. When I get here, as soon as I touch Rothera, I'm in the field. We are here to do year-round marine research. We go out in small boats and we measure the health and the biology in the ocean and the oceanography in the ocean around Rothera. We've been doing this for 25 plus years. So we have this long-term continuous year-round research, and we're trying to understand how the animals living in the ocean are adapted to life in the constant cold of the Southern Ocean, but also with this massive seasonal variation that Nadine and Roseanne have already talked about, where we go from 24-hour daylight to 24-hour darkness, where there's massive amounts of food in the form of this phytoplankton, this algal column that is available for the animals to feed on during the summer, but in the winter, for up to 7 months, things like sea cucumbers, which feed on this phytoplankton, can go for 7 months without any food at all. The sea freezes over in winter, like Nadine and Roseanne were talking about, and that affects how much energy comes into the water column. So we're here doing this research, and we need to understand how the animals survive in this ocean, but we also need to understand how it's changing and how that change will affect the animals. And Dave here will talk to you a little bit more about this change.
So as you've heard, one of the many things that makes polar seas special is the freezing of their sea surface into what's joined into land called fast ice. And this means to scuba dive below it and explore, as Simon and I do, we have to cut holes in it with chainsaws to see the life underneath. Now, one of the most visible responses of the Earth to climate change has been the losses of that freezing sea surface. And you've seen animations earlier to show that. And that's changed the amount of heat being absorbed by the planet, and also the amount of light and energy reflected back into space. And many animals and algae that you've heard various people talking about have that ice as a home. It's part of their habitat. And so that for them is loss of their habitat, which is changing both their abundance and their distribution, where on Earth they live. And so less frozen sea surface also means some other things that you might not think about. Icebergs get frozen into that fast ice and locked in place so they can't move around. And when they move around in wind and currents, they can collide with the seabed in the shallows. And that means that they kick up large areas of the seabed, they reshape the seabed, and they kill the life on it. And that means that life on the seabed in the shallows is a sort of patchwork mosaic of things that were hit maybe last year, maybe the year before, maybe 10 years ago, maybe hundreds of years ago. And so it becomes a really weird landscape of a sort of a map of when it was last hit by icebergs. And that's something that we study here with a grid of markers on the seabed. And both Simon and I will be diving on that next week. But conversely, when sea ice is lost, algal blooms can take place, and that carries carbon. They fix carbon from carbon dioxide in the air. They transfer it to the food web, and that can ultimately, on death, be transferred into sediments below. And that's a very important place called a carbon sink. And this is one of the only places in the world where some carbon sinks are actually increasing in response to climate. But that only works if it's protected. So as fjords emerge from glacier retreat, if they can be protected from human impact, then they can work to help with us combat climate change. And so it's a really important area to map these new emerging carbon sinks and put protection in place so that they can help us. And back to you.
Thank you very much. I don't know if you can hear us. Can you still hear us? Are we still there?
Yes, here we are.
Thank you so much. You know what's amazing? We hear so much about climate change, but actually meeting the people who are on the front line, gathering the data so we can understand how we know what we know is terrific. So thank you very much. We've got some questions, I think.
Loads of questions are coming. I'm so sorry we don't have time to ask all of them. But I just would like to ask as many as possible. One really great question that we had was, what is the minimum size of an iceberg? I wonder if Anne is online who could answer that. Yes, maybe it's this. Is there a minimum size for an iceberg? Anne, are you there?
Sorry, I couldn't hear. Can you
yes. Our question is, what is the minimum size for something to be called an iceberg?
Oh, yes. So I don't know the exact definition. I think you call an iceberg already an iceberg when it's a few meters long.
Okay.
And I can say in the Arctic, icebergs are also classed into the smallest one as a growler, and then there's different kinds of icebergs, also depending on the shape. The tabular ones are the ones that we have in Antarctica, for example, but they can also be pinnacle shapes or domes, or like have all sorts of forms. And in the Arctic, there are real size classes. You call them small, medium, large, and so on. But in the Antarctic, we just came up with this word giant because they don't fit into any of the size classes, because they were all meter scale, and in Antarctica we're talking about kilometers of length. And
Understood. Oh, thank you so much for that answer. There's lots of questions about icebergs going on. I think one of the great things about being in Antarctica is watching icebergs float past your ship. It's really quite incredible. I
love the language of icebergs. Things like growlers and things like bittybergs, and there's all kinds of weird terminology that I didn't know anything about.
Another quick one for David and Simon, if you're still there. People are really curious about the minimum temperature that has been observed in Rothera this year. So if you're there, perhaps you can tell us what the lowest temperature is. Well, now we're in spring, but we've just come through winter. David and Simon, are you there?
Yeah, we are. That's a little difficult for us because we only arrived 2 weeks ago. Disingenuous of us, but normally it gets to about -30 or thereabouts over winter, the air temperature. Obviously the sea doesn't get below about -2 because at that point it will freeze.
And then I guess with the wind chill, obviously it feels much colder when you're out there as well. You need lots of layers on. One more for you actually, that people have been asking about ice ages. So we know in the history of the Earth we've had...
Not the movie.
Not the movie. We've had ice ages and the ice has expanded and receded. And people were wondering whether we expect there to be another ice age at some point in the future.
No, I think we can confidently say that's quite unlikely. The temperature is going to follow carbon dioxide and other greenhouse gas levels, which are unprecedentedly high in times measure. And so that's going to keep ice receding, and our job really is to try and reduce those and to reduce the ice loss. But I think we're a long way from approaching another ice age.
All right.
Good
Thank
questions.
You so much.
Thank you so much, and good luck. I think I heard you say you're going to be diving under the ice soon. I can't think of a more extreme job than that. Maybe McGann being an astronaut might be as extreme, but good luck with that. Right, what have we got coming up?
Yes, well, we're moving from ice to oceans very shortly, so do join us for the next session. In the meantime, check out social media, #POP23. Let us know what you're doing in your classrooms. That's @Esero, ESERO_UK. We'd love to hear what you're up to. And don't forget to join us again. In just a couple of minutes, we'll be talking all about the oceans.
See you later.
Bye.